So why you do girls like that, guys? I got this question for a real long time.
When the LED is set up within the integrating sphere, we would change the voltage with this, and as you can see, as the voltage is being changed, the power is greatly increasing. Our dark reading was 81.8 microwatts, and with the laser set up in the integrating sphere, we now have a reading of 82.8 microwatts, showing that the laser is very low powered.
Here's the power versus voltage curve for the blue LED. You can see that once it is on, you get a very ohmic response. Compared to the laser diode, which only produced a net power of about 1 microwatt, the blue LED produced a peak at almost 1 milliwatt.
So for the radiance bench, we used the LED and the LD, and the first lens would collimate the light source, while the second lens here would focus the light source down onto the detector, and then we would put the polarizer onto the rail as well, and measure the peak-to-peak voltage as a function of the angle of the polarizer.
Here we are measuring the beam divergence for the LED and the laser diode. In blue is the LED and orange is the laser diode. Clearly the LED has a much broader divergence than the laser diode. The laser diode drops off intensity very rapidly, whereas the LED has a much wider source cone than the laser diode. We use the 1 kilohertz source generator to power both the LED and the LD, and use the rotating stage to measure the divergence of the beam, and we measured the power on the power meter, and we were able to determine the divergence of both beams. Here's the laser diode response to the changing angle of the polarizer, and as you can see with this oscillation, that means the laser diode is fairly polarized, compared to the LED, which had a peak-to-peak voltage which stayed entirely constant through the rotation of the polarizer, meaning that the LED is essentially a completely unpolarized source. Below the threshold current, we see the small peak of the spontaneous emission. As we increase current, we start getting more spontaneous emission until we get to around 23 milliamps, where we see the stimulated emission. You can see this infrared peak as well, and the peak broadens quite a bit as we get to lasing. The spectrum of the LED is much broader than the laser diode, and as we increase the voltage, we get a much broader beam, and the peak shifts to lower wavelengths. Here's the spectrum width versus drive current for the laser diode. As you can see, before lasing at about 0 to 23 milliamps, you have spontaneous emission. After lasing, the spectrum broadens quite a bit. However, this is just the spontaneous emission background. The actual lasing peak remains fairly narrow. Here's the spectrum width versus voltage for the LED. As you can see, the LED turns on about 1.5 volts, and the spectrum stays fairly broad with increasing voltage.